Hi, I'm Luke Kane. Welcome back to Statistics. Today we're going to talk about the normal distribution. And that raises the question, what do we mean by normal data? Is there such a thing as abnormal data? Well, I don't think so. But normal data is data that tends to cluster around a mean, that tends to stay pretty close to an average. And a couple of examples. Measurement errors are a good example. In fact, one of the first uses of the normal distribution was to calculate the distribution of measurement errors of astronomical observations. But it fits many different kinds of measurements. Measurements of women's heights, measurements of men's shoe sizes, things like that. They also fit a number of natural phenomena. For example, cholesterol levels in the blood usually fit a normal distribution. The radioactive decay of an isotope fits a normal distribution. But the real reason that we spend time on the normal distribution is because sample data tends to fit a normal distribution, and hence I like to think of the normal distribution as the mother of all distributions with respect to statistics. Now, the history of the normal distribution is quite interesting. It starts with Abraham de Moivre, and de Moivre was an 18th century mathematician who did some consulting work for gamblers, and he was working on the binomial distribution, and of course, he was working on it long before there were calculators and computers, and a distribution that's of great interest to gamblers, of course, is the binomial distribution, which we've discussed in the past. And he was looking for ways to calculate the binomial distribution with a very large number of trials, which is of great interest to gamblers. And of course, it's a difficult problem to do by hand. And he discovered that the binomial distribution, as you do more and more trials, tends to look like a curve, continuous curve, and he applied it to that particular problem. Unfortunately, de Moivre didn't publish. He left it in his personal notes, which were discovered sometime after he was dead. One of the first to publish was Johann Carl Friedrich Gauss, a very famous mathematician of the 19th century. He was so famous that the Germans, in their pride, actually put his picture on currency, which I find rather interesting. Only instance I know of mathematicians whose picture got on money. Anyway, that's how important Karl Strauss was. And he discovered it independently of de Moivre. And as a result, since he was the first to publish about it, it's often called the Gaussian distribution as well, but it's the same deal. So what we're going to do is look at some of the properties of the normal distribution. We're going to look at its shape. We're going to look at some mathematical properties, and then finally we're going to talk about perhaps the most interesting and most useful aspect of normal distribution, and that is that when we compute the area under the curve of a normal distribution, we're actually computing a certain type of probability. So let's take a look at the normal curve. This is the normal distribution. It is a plot of the function that appears in your lower right hand corner of your screen, where y of x is your dependent random variable and the independent random variable is x. Alright, now notice that this particular number is bell-shaped. I mean, it's not exactly the Liberty Bell, but it's pretty close. And it doesn't matter what I do to the two parameters, it's still going to retain its characteristic normal distribution. So let me put in just to help illustrate. Let me show you the mean. Here's the mean. All right, and I can move the mean anywhere I want, to the left, to the right. The mean can be infinitely large, can be infinitely smaller, and still the curve is bell-shaped. Same is true for standard deviation, although it's going to get a little, it's going to change. As the standard deviation gets higher, the data set is being distributed in general farther and farther away from the mean, so it looks flatter and flatter, but it's still a bell-shaped curve. No matter what we do, it's still bell-shaped. All right, let's look at this mean. You'll notice the mean here is the highest number, right, in this curve. It's going to be the highest point in the curve, which suggests that the mean is also the mode. And if you'll bear with me for a minute, I'll try and demonstrate that the mean is also the median. Now, to understand that, we have to understand that the way we use the normal distribution is to calculate the area under the curve. And that area under the curve is going to represent a set of probabilities. So, for example, all right, I have the area under the curve from x equals a to x equals b. Well, that area is 0.26. That means that the probability that x is between 0.55 and 0.8 is 0.26. Now let me take this left-hand limit here, the lower limit, the lower bound, and let me extend it. Now watch what happens. As I keep going to the left here, this doesn't change. So in effect, this could be negative infinity. So basically what this is saying is that the probability that x is less than the mean, that's 50%. So by definition, that means that the probability that x is greater than the mean is also 50%. So that tells you that the mean is the same as the median, since half of the population is below it. And one last thing about the shape of this curve. Let's get rid of the area. Now what I want to show you is 2 points on the curve. Okay. Let me put this over here. All right. This point y is reflected across the mean to the point y prime. So you'll notice wherever I move y, y prime has the same value. Doesn't matter where I do that. Well, what that means is that the curve to the left of the mean is a reflection of the curve on the right of the mean, which means that this curve is symmetric. Okay, so now let's look at some mathematical properties of the normal distribution. All right, here's x. X is our random variable that appears here. It's an independent random variable, and as we mentioned earlier, it can be anywhere on this curve. And of course, associated with that random variable, there's a y. So you'll notice everywhere I go, no matter what x is, there's a corresponding y. This means that this is a continuous function. It's a continuous distribution. Let's compare that to the discrete distribution that we studied earlier, the binomial distribution. Remember there, x was the number of successes in a given number of trials. X had to be an integer, and it had to be a positive integer or at least 0, because it didn't make sense to talk about negative losses. That's what is that? I mean, I don't know what that is. And it certainly doesn't make sense to talk about 3.5 losses. But however, x can be anything. So if we're talking about our cholesterol levels, our cholesterol level might be 80 micrograms per deciliter, or whatever is the measurement. Or it could be 80.1, 80.7. It could be the square root of 933. I don't know that much about physiology, but the point is that it can be any number on a real number line. It is not constricted in that regard. So this is a continuous function. Now, as you can see, since x can be anywhere, the domain of x is x can go from negative infinity to positive infinity. What's more interesting, however, is the range of y. Y is always greater than 0. Well, that doesn't look the case when we go to the left. When we go to the left, you'll notice the curve looks like it's touching the x-axis. Now it's getting closer and closer to the x-axis, and eventually we get to a point where, wait a minute, it seems to have touched the x-axis. Well, that's an illusion created by the limits of this graphing program. This graphing program can only display a number to 1, 2, 3, 4, 5 with up to 5 decimal points. Let's see what y of x would actually be at -2, and to do that we can do that with our calculator. So we pull out a graphing calculator. This is a TI-84, and we go to distributions. We hit the second button and VARS, and you'll see there's distributions. And the number one is the normal probability density function. That's just another name for this normal distribution. So we hit enter. And what's our value? Well, our value of x is -2. So we hit enter. And the value of mu is 0.8. That's the mean. And the value of the standard deviation is 0.35. We hit enter. Now we paste that into our main window. Let's double check. The x is -2. The mean is 0.8, and the standard deviation is 35. That's correct. So let's calculate it. Oh my goodness. Look what this says. This is 1.44444 blah 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 times e, in this case 10 to the -14. Well, let's see what that looks like. All right, if I were to put that in decimal notation. So I have y of -2 equals, now I'm going to have to count 13 zeros. So let's count out 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And now we can start putting in the numbers that a calculator gave us that are not 0. 1, 4, 4, 3, 5, 0, 6, 0, 2, and so on. I suspect this goes on to infinity. So you'll notice at x equals -2, y is not 0. It is a very tiny number. It is very close to 0. It looks like it's going to get to 0, but the reality is it never does. That no matter how far I take x, y of x is always going to be positive. It is never, ever going to be equal to 0. And now finally, let's look at some characteristic probabilities of the normal distribution. We've already demonstrated that the probability that x is less than the mean is 50%. Let's put in some standard deviation. So here's, this green is the standard deviation, one standard deviation away from the mean on the left-hand side. So let's see what that area is. That area is 34%, which is typical of a normal curve. If I look at the area between the means, that tells me that the probability that x is between one standard deviation to the left and one standard deviation to the right, that's going to be 0.68. Actually, it's going to be a tiny bit higher. It's 0.6812, blah, 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 blah. But 68% is close enough for government work anyway. And no offense to government workers. My father was a postman, so he used to tell me that all the time. Anyway, let's go over another standard deviation, see what we get. Alright, so now we're going to go 2 standard deviations. And if we go 2 standard deviations, it's 95% roughly. It's going to be a little bit higher, like, I don't know, 95.3%, something like that, and so on. But it's 95% of your population is going to appear between 2 standard deviations of the mean. And if you were to keep going, and we wouldn't see it here because it's so tiny, if we go to 3 standard deviations from the mean, the area 3 standard deviations of the mean on the left-hand side to the right-hand side is about 99.7%. We learned some properties of the normal distribution. First, we learned that the shape of the curve is bell-shaped, and it is always bell-shaped regardless of what happens to the mean or the standard deviation. We learned that the mean, the median, and the mode are in fact the same number for any normal distribution. and we learned that the distribution is symmetric about the mean. We also learned some mathematical properties of a normal distribution. We learned that the function y of x is continuous. That is, when we plot it, there are no gaps at all, unlike binomial distribution, which was a discrete distribution. The domain of x can then be any real number, going towards negative infinity or positive infinity. And the range of y is any number greater than 0, but it can never ever equal 0, which is, I find, somewhat remarkable. We showed that even a short distance away from the mean, that in fact the y value gets to be very, very small. What else do we learn? Well, perhaps the most important thing we learned is that the area under the curve represents probability. Not the probability of a single event. That's something we cannot determine from the curve. We can only determine the probability that x is between two values, or less than some value or greater than some value. So we discovered that the probability that x is less than the mean of the distribution is always 50%. The probability that x is around the mean, give or take one standard deviation, is about 68%. The probability that x is about 2 standard deviations away from the mean, give or take, is about 95%. And although we couldn't plot it, the probability that the mean is within 3 standard deviations, that x is within 3 standard deviations of mean, is 99.7%. Okay, this is nicely summarized in this table, which you should be very familiar with. And next time we're going to talk about a standard normal curve. And that's a curve in which the mean is set to 0 and the standard deviation is set to 1, and you can convert any normal distribution to a standard normal distribution by calculating its z-score. And when you do that, the z-score actually tends to tell you two things. One, what side of the mean is it? So if it's negative, it's on one side. If it's positive, on the other. It also tells you how far away from the mean it is. But we'll get into that next time. Till then, I'm Luke Kane. Thanks a bunch for watching.